So in the last class, we have mentioned that this one we will start with uh, natural convection. So far, we have understood what is a forced convection because there was the velocity which drives the flow, and for that, the heat transfer coefficient has a significant value, or say the convection was moderated by that external flow. Now, the point is that if we remember that this Nusselt number, or in other words, say the convective heat transfer coefficient, it is strongly dependent on the fluid velocity or the medium velocity in which this convection heat transfer is happening. If you remember the relation, that Nusselt number was a function of Prandtl number and Reynolds number. So Reynolds number is the part where the velocity is clubbed, and if you increase the velocity, Reynolds number increases, and so as the heat transfer coefficient. So now when we talk about, say, natural convection, when there is no external flow, externally, say, driven flow. Okay, there is flow around that object which we cannot see, okay, or even cannot feel in certain cases, but there the flow exists. But that flow is typically not driven by some external force, which is there and apparently visible in case of external convection. So that means the fluid velocity, or say the fluid motion in forced convection, is strikingly noticeable. For example, there would be a fan or pump to drive that fluid. But in natural convection, or say other words, we call that as free convection. Okay, so we say that free convection or natural convection. In this case, there is no such external means by which the fluid is driven. So quite naturally, you can understand that if the fluid or the medium velocity is zero, I mean, not zero, non-zero value, but it's lower and substantially lower than forced convection cases. So that means that heat transfer coefficient in natural convection would be much lesser than that of the forced convection. So why we still need to understand that? Because there are several natural phenomena exist where the heat transfer happens through this natural convection, and there are places where you really cannot place any external mean to drive that fluid. Okay, there are several integral traces where, for example, your computer PCB, or say the motherboard, etc. Although there is a small fan exists in certain cases, but there are several places where the flow cannot be externally driven. So in those cases, several innovative geometries comes up. Okay, several innovative geometry have been developed to enhance this heat transfer for our computer or laptop cases, in order to cool off the motherboard, PCU, and all this PCB and all this part. Okay, so that means we will see today. In fact, we know a couple of examples of this natural convection. For example, when you have, say, a cup of tea or a cup of coffee that is placed in a quiescent room, in a simple. There is no fan is running, no AC is working. Just put it in ambient temperature. Okay, so eventually that liquid will come to ambient temperature after a prolonged period. Now, in such cases, or say a ball of some metal, okay, that is say essentially was heated, that has a certain temperature, and then this one is placed in ambient on a table, ambient temperature. Okay, so in this case, how the heat transfer will happen, except if we do not consider say the radiation. There definitely would be radiations, but say for the time being we neglect the radiation. So the mechanism of heat transfer in such cases, that when it is exposed to the this ambient temperature, okay, or temperature that is cooler than this ball temperature, what will happen, that the temperature of this surface of this ball, okay, so this surface will immediately drop to a temperature, okay, that is not equals to the surrounding temperature, higher than that, but not definitely say the temperature that is at the center of the ball. Okay, so the center of the ball will have the highest temperature at that time, and then gradually we see a temperature difference from the core to the surface, and from surface to the ambient fluid, or say the air in this case. So the air that is adjacent to this ball, that is surrounding to the surface of this ball, will gain some temperature immediately. Okay, and remember, there is no external flow. That means no air is forced to flow over this spherical ball. Okay, there is no such cases. So what will happen now, due to conduction from surface to this nearby fluid layer, the heat transfer will happen. That is a very thin layer. So that will create a kind of a encapsulation of around this spherical ball that would be made of a thin layer of air. Now you have a cooled water, or say the cooler air surrounding to the surface. So this thin layer will actually interfere in this cooling process, okay, because this is now blanketed by a warm air layer. So there is no direct contact of this cooler air to the surface of this ball. Now, what will happen, that this gaseous phases, their property, particularly the density, significantly changes with the temperature difference. So what will happen, that as soon as the air comes in contact with this thin layer of hotter air, what will happen, its density will go down. Okay, and then comes the influence of gravity or gravitational field. What will happen, once the density decreases, it will try to go upward. Okay, so say the nearby fluid that tries to comes now within the enclosure, okay, those will be heated and go in this upward direction. Okay, so the air that comes in contact with these surfaces will try to go in the upward directions, and eventually there will be a fluid, or say the air motion, which is like this, will be going upward. So these would be the warm air and these are the cool air. So the heat transfer will happen from the surface to the stream of the air. Now this motion we really cannot visualize. If the object is small, we cannot really visualize or feel. But if the object is substantially large, there would be a demarcation. You can feel it in certain cases. You see that nearer to that, it's a bit hotter, and there is a movement of air. You feel that. Okay, so here, despite having any means of transporting the fluid or fluid driving force, here the gravitational field is what imparting this fluid motion or dictating this fluid motion. So we will have a situation where, say, the low density or the light air would be surrounded by high density or say the heavier air. And the natural law, we know that the lighter part will rise. Okay, so it's a kind of a thing that if you try to mix oil and water, the lower density fluid will try to float above the higher one. So this stream or this current we call the natural convection current. And this mechanism of heat transfer, we say the free convection or the natural convection of heat transfer. But here again, you remember that in absence of any natural convection, the heat transfer from this spherical ball to the air surrounding is by only conduction. If the natural convection is not there, if you do not have a medium or a fluid medium where you have kept that ball, if that is a vacuum, then except radiations, we are not considering radiations at all here. So then the entire heat transfer is by conduction only. And then what would happen? The rate of heat transfer from this ball would be further lower than that of this combination of free convection and conduction. Okay, so for example, the similar, say the practical cases that we, as I mentioned, a cup of tea or a Coke can, when you place it in your room, where say there is no air circulation, but still it will come to the ambient or the room temperature after a prolonged period. So since here the gravitational field is actually what is dictating this natural convection current. Okay, so in a gravitational field, so what will happen? What is the net force that acts on a body? Can anyone tell me? You have heard certain principle on this natural, on this say gravitational field. You remember the Archimedes principle, right?
Yes, sir.
Okay. So the point there, what you have heard a force term. You remember what is that force called? Say,
Buoyancy.
right. So there would be an upward force exerted by a fluid on a body that is completely or partially immersed in that medium. So you have a pool of liquid, and there you have a say partially immersed or fully immersed body. Then it would feel a force that acts on its normal direction. Okay, so that is called, the spelling is Bouyancy, buoyancy force. Now this force will have a magnitude that is equal to the weight of the fluid displaced by the body. So if I write FB, okay, that is the density of the fluid, G, gravitational field, and volume of the body. Okay, so here this rho fluid is the average density. Remember, it is not the density of the body. G is the gravitational acceleration, and this V body is the volume of the, say, the certain portion of the body that is immersed in the fluid. So in case of completely immersed body, it is the total volume of that object. And say if we do not have any other forces, okay, so there is a weight force that is acting on the body, and we have FB that is acting upward on this object. So in absence of any other external forces, okay, so the net vertical force, or the force in the vertical direction, okay, on a submerged or fully immersed body would be F, say, net force is the weight minus FB. Now the weight is rho of the object. Okay, so I would say let's write it clearly so that there is no confusion. So rho of the body or the object, and G, fine, and the V of the body, the volume of the body. That gives us the weight of the complete object. And the buoyancy force is this value, which is rho of the fluid, G, and V of the body. So that means what we have is the difference, density difference of between the body and the, or the object and the fluid, multiplied by G and the portion that we have, the volume of the body. Okay, so that means this, the net force is basically proportional to the difference in densities of the fluid and the body that is immersed in it. Therefore, what we have, the body, say, or the object that is immersed in a fluid will actually experience some weight loss. And that is the Archimedes principle, that the weight loss would be equals to the weight of the fluid that it displaces. Fine? Any question? So say it's in a household thing or experiment we do to check, say, the quality of egg. Okay, so the egg, if the egg is fresh, can anybody tell me what would happen if the egg is dropped in a bucket of water?
It will float.
Yeah, Devesh, go ahead.
So because the I mean the
Not because
density is
no, at first still what will happen after that the because. So what will happen if you buy egg and then you put it in a bucket of water? What will happen? Raw egg. Will it float? Will it sink? Will it be submerged or kind of go down at the bottom of the bucket? What is your experience? Has anyone done
sir,
it or
sir, it
checked
will
it
float.
ever? It will float.
Yes, sir.
And if that floats, then what is the quality of that egg? Is it good or bad?
It is good.
Sure.
Yes, sir, sure.
So the point is that the average density of egg is somewhat greater than the density of water for a fresh egg. That is a good quality egg. So the egg will settle at the bottom of the bucket. If not, if that is rotten, it would typically float. Otherwise, what also can happen if it is kind of intermediate scenario, then the density of the egg somewhat or the average density of egg is equals to the density of water. It will be somewhere in the middle of your or say anywhere in between the bottom wall. It would not touch the wall, the bottom say the wall, and not even it will completely float. So it would kind of a weightless object. It would be there. That's the case. So the point is that without this buoyancy, okay, heat transfer between a cold surface and the surrounding fluid would be by pure conduction. Fine. So the point is that there is no gravity in space, and therefore there cannot be any natural convection of heat transfer in any of those spaceships or spacecraft. That is really, even if it is say, if you fill that with say atmospheric air. Okay, so that means in all the studies, in on all the cases, our main thing is the temperature. And now we have say the buoyancy force. So how do we relate these two? That how buoyancy force now can be related with the temperature. Okay, so that means now buoyancy force, if you now look at this expression, this buoyancy force, you can relate with the density difference. Now the temperature and density has the relation. Okay, so if you find out, or if we find out a way in order to express the variation of density with temperature, keeping the pressure constant, because if that also changes, then the situation becomes more complex. So say for a constant pressure scenario, if you know the density variation with temperature, then you find a relation between the buoyancy force and the temperature indirectly. Now, the property that provides that information, that is the density change with temperature, we call that as the volume expansion coefficient. Volume expansion coefficient. Or the symbol is beta. And this is defined by this is rho del rho by del t at constant p. This has a unit which is 1 by k. Okay, so the volume expansion coefficient. Now, one thing you can immediately tell me that if the fluid is ideal gas, then what is the volume expansion coefficient? For ideal gas, what is the value of beta? Can someone tell me? This is the
RT,
expression. Sorry?
RT by rho.
RT by rho. The beta, I'm asking directly the value of beta.
Oh, it will be RT minus RT.
Sure. Just check once again the calculation.
Sir, 1 by t.
Absolutely. Because the hint was already there when I wrote the unit, and that is why I asked. Because see, for the ideal gas, rho is basically P by RT. If you replace that in now in beta, what will be there? We have P by RT square. And again, P by RT is rho. So you have, sorry, this would be not minus, this would be plus because it is the derivative with respect to for 1 by t. So it is minus 1 by t square. So minus minus would eliminate. So here that means you have 1 by rho multiplied by rho into 1 by t. So it is essentially 1 by t, where t is, remember, is the absolute temperature. Because you are using P by RT for the ideal gas scenario. So for ideal gas, if the temperature is known, you can quickly calculate the value of beta. Otherwise, the table or say some reference would be given in order to know the value of beta. Okay, so now say this beta, when we write this, now if we replace this differential quantity with the difference, considering say we have a surface, and so now the point is that one thing I have not told you, but which is very implicit, is that when this convection is happening, so near the wall there exist boundary layers. Now what is your intuition or say the physical insight on the phenomena now, that because you know how the boundary layer develops, can anyone tell me what do you expect the thickness of the thermal boundary layer or say the boundary layer in general? in case of natural convection versus forced convection? Which one did you expect to be thicker or thinner, and why?
So the boundary layer of the natural convection will be more than that of the forced convection.
More means more thicker, right?
Yeah, it should
Yeah.
be more thicker.
Right. Because there is no flow, no external flow as such. Okay, and we have seen in external flow cases that when you increase the flow, the turbulence in the turbulent region, the thickness becomes smaller or the thinner and thinner. So that means if you decrease velocity, it is becoming more thicker and thicker. And here there is no external flow, so it would be somewhat greater than the forced convection cases. So say we assume that at sufficiently far from the hot or cold surface on from which the natural convection is happening, we again designate that with the say suffix infinity or superscript infinity. Okay, and we express beta, or say now it is not equals exactly equals, because we express that with a difference. So this is what we are trying to write. At constant p. Where this rho infinity is the density and of say the fluid at t infinity. Okay, and T infinity is the temperature of the quiescent fluid away from the surface. Okay, so there, if the surface is say apparently this one where the convection is happening, so far away from here, there you would not feel any convection current. And at that position, we are considering that's a far away from the cooling or the heating surface where the air is calm or quiescent. Okay, so that means now what we can write is that minus rho is basically rho, and then we have a beta t minus t infinity. At constant pressure. So the density difference and the temperature difference, we express that in terms of the beta. So what would happen if the value of beta is say large of a fluid? What does that mean? From the expression, what do you expect? If the beta is large, what will happen? Or what does this mean for a fluid?
It expands rapidly at even small changes of temperature.
Temperature, absolutely. That means there would be a huge jump in density with respect to temperature at constant pressure. And this product that we have, that is the beta delta T, this actually is the portion of volume change, or the fraction of volume change, okay, with the change in temperature. That is the measure at constant pressure. So now if we go back to our problem, or what we started, is that the buoyancy force is proportional to density difference. Now this density difference is now proportional to the temperature difference at constant pressure. So that means if there is a larger temperature difference between the fluid that is adjacent to a hot or cold surface and the fluid that is far away from it, then there will be the larger buoyancy force, and we will have a stronger natural convection, or the free convection current. So the higher heat transfer rate can be achieved. Okay, any question with the concept?
No, sir, no questions.
Okay, thank you. Okay, now say the point is that the magnitude of this natural convection, okay, between the surface and its adjacent fluid, is basically say the function of this convection, the natural convection current. So as you increase that current, there will be the higher heat transfer rate. Okay, but the point is that it is still lesser, since there is no blower, no fan, or that kind of thing is being used, or externally controlled devices or drives are being used. Okay, so it would still be lesser than the forced convection coefficients. Now, say whenever we have two objects in contact, be it say solid, liquid, fluid, this combination, whatever, and it moves, say, relative to each other, we have a friction force that develops in the contact surface. Okay, so this force actually slows down the movement of the fluid, and so it basically reduces this current rate, or the flow rate of the fluid that is being convected with the help of natural convection current. So that means, say, we have, in order to increase the heat transfer rate, if we by now you are aware of the concept of FEED, right? The concept of extended surface. Now, as you increase this extended surfaces, the fluid is moving over this extended surface. Now we are focusing on the natural convection part only. Remember, there is no external fan or no external blower. So that means there is a kind of a two opposite thing that could happen. One is the friction force that would limit that the natural flow of the convective current. But this natural flow is needed in order to enhance the heat transfer rate by natural convection. So that means there is a balance between this friction force and say the buoyancy force, because buoyancy force eventually dictates this natural convection current. Okay, so now say the density difference that we are considering, that this rho minus rho infinity, that is say the density difference between if we consider, say now we consider a plate, say a vertical plate. Say we have a vertical plate. So we have a vertical plate like this. Okay, then this vertical plate is say exposed in air, ambient air or some fluid. Okay, and there is the temperature difference between the vertical this wall and this surrounding media. Now let's assume, in order to simplify the scenario, that we have it's a steady state scenario. Okay, there is the laminar flow, which is quite logical to assume for the case of natural convection flow. Say it is two-dimensional for the time being, and the fluid is Newtonian, or the surrounding media is Newtonian, where we have all constant properties, including, which is kind of a contradictory, you realize, but the density we are assuming it to be say constant when we have in the free stream. Now here there is the free stream means far away from the surface, the considered surface. As such, that is not a free stream one, but at the infinity location where we have a quiescent air. Okay, but there is density difference, because that is what drives the natural convection. Okay, so we will have a boundary layer. Say if I draw from here a boundary layer like this, the surface, and say for the sake of simplicity in calculation, the directions upward, it's say the x directions, and the normal direction is the y. Here we have stationary fluid or the stationary liquid, whatever. This is the boundary layer. Okay, so what will happen, how the velocity profile would be? Our usual consideration is u is equals to 0. Okay, on the surface. Can someone tell me what would be u here? Here in this crosshair that I mentioned, these positions at the boundary layer or just outside the boundary layer, what would be the u? U is equals to
0.
0, because this is the stationary fluid, that is the consideration. Okay, so the velocity profile would have a tendency that would look like something like this kind of a thing, that from 0 it would start, and then somewhere in the middle there will be a higher velocity or the highest velocity. And then you have a plateau which goes to 0 at the surface. What would happen with the temperature? How the temperature profile would look like if I consider this T surface is higher than that of the stationary fluid, which is T infinity. See, here we have the temperature, which is T infinity. How the
temperature should asymptotically decrease to T infinity from the surface.
T, absolutely. So say it is something like this. So the temperature drops to T infinity from Ts, where this Ts is the wall temperature or the surface temperature. Okay. Now, this is the vertical surface that is being cooled by natural convection. Okay. Now, if we consider a small elemental, say, volume element that is of, say, dx, dy, and dz. Here we are considering, say, two-dimensional case. So this is, say, the dx, and this is the dy. The forces that acts, we have, say, the tau, shear stress, tau plus d tau by dy, del y by del y, and dy. Here we have, say, the pressure, and this is the pressure plus del p by del x to dx. Okay, and now if this elemental volume, the differential elemental volume, if we consider for analysis, and the force that is acting on this element, if we balance it by the Newton's second law, okay, that is, say, its mass and the acceleration in the x direction is the total force on the x direction, where delta m is nothing but rho into dx dy, and, say, the unit depth in the other direction. This is the mass of the fluid element within the control volume. And the acceleration du by dt, okay, which is del u by del x dx by dt, if we take the total derivative. Which means we have u del u by del x plus v del u by del y. And the overall force that is acting in the x direction, it's this minus this plus this minus this. This difference between the shear stresses and difference between the pressure forces. If we add those two, what we have a relation that would look like, that is, now this force, this is the net tau shear stress that is acting on the surface area dx by 1. If we look at the figure, then it would be pretty much clear. This by x dx, this is the net thing that is acting on dy1 minus rho g dx dy. That is a net force acting on this differential element, where in this case it is pretty obvious that tau, since we are considering this as the Newtonian fluid, we have tau is equals to mu del u by del y. We substitute that in this expression and then equate this. That is, del is this one, a is this one, and fx is this one. We will have the conservation of momentum in x direction, which would look like rho. Now you have seen this form. Minus rho g. So conservation of momentum of the fluid in free convection in x direction. And if we apply this equation outside boundary layer, what we have to do, the final question, after this we will stop. If we try to apply this equation outside this boundary, that is in the quiescent or the stationary fluid, what will happen? Or what we have to...
So there u will be 0, so equation will reduce to dou p by dou x is equal to minus rho g.
Absolutely. So this would happen. Now, since it is the free or stationary, let's designate that with the p infinity. If you place u is equals to 0. Now, this is simply, say, what is this expression? Can somebody remember? Somebody remembers that how to calculate the pressure difference between two places? The hydrostatic pressure equation, the variation in hydrostatic pressure in a calm scenario. That is simply varies with height, rho g h. Clear? Any question? Any doubt? Fine. So we stop here today, and the next week we'll pick it up from here, from these governing equations, and we'll see a couple of problems related to free convection. And in the next class itself, we will complete this free convection chapter. Because here again we will see several empirical relations, because theoretical derivations of free convections is very much dependent on the scenario or the shape or the particular object. So similar to forced convections in other cases, I will show you a couple of relations, empirical relations that best describe certain scenarios. And we have to find out the best scenario for your problem to find out the Nusselt number and subsequently the heat transfer coefficient and so as the heat transfer rate that we follow. Okay, guys, thank you then.